Section: Introduction. In this section, we discuss the current trend of using large batch training for large language models, which has become the standard due to advancements in deep learning hardware. For example, the Olmo 65B model employs a batch size of 2048 sequences, leading to a total of 4 million tokens per batch. While this approach effectively utilizes hardware through parallel processing, it presents a significant challenge known as the generalization gap, where the model's ability to generalize diminishes compared to smaller batch training unless we carefully adjust other hyperparameters. Research suggests that small batch methods often lead to better generalization by converging to flatter minima. To address the generalization gap, some studies have recommended using larger learning rates to counterbalance the effects of large batch sizes. However, training models based on the transformer architecture can be unstable, requiring careful tuning and selection of hyperparameters, such as opting for smaller learning rates. Additionally, we explore adaptive sampling methods, which adjust batch sizes during training to enhance the accuracy of gradient approximations. While previous work has focused on single device settings, this limits their applicability in distributed training environments where data is spread across multiple devices. In distributed training, particularly with data parallelism, each worker maintains a local copy of the model parameters. The global input batch is split into smaller batches for each worker, which then synchronize gradients after each training step. We can develop adaptive batch size strategies for data parallel settings, enabling the training of large-scale neural networks. Despite these advancements, training state-of-the-art large language models, which can have billions of parameters, poses challenges due to memory constraints. Many researchers have limited access to high-memory GPUs, leading to the exploration of model parallelism, where model parameters are divided among different workers. PyTorch's fully sharded data parallel, FSDP, is a notable implementation that supports models with trillions of parameters without needing complex third-party libraries. However, even with data and model parallelism, pre-training large models remains costly and environmentally impactful. Therefore, we emphasize the importance of developing effective training strategies, particularly focusing on dynamic batch size schedules. These schedules are crucial as they influence both training efficiency and model performance, yet current practices for selecting batch sizes often rely on heuristics, which can be challenging to optimize. Section Summary. In this section, we discuss the challenges and strategies associated with large batch training for large language models, highlighting the generalization gap that arises compared to small batch training. We emphasize the need for dynamic batch size schedules to improve training efficiency and model performance, while addressing the limitations of existing data and model parallelism approaches in handling extremely large models. Section: Contributions. In this section, we outline our contributions. We propose adaptive batch size schedules grounded in theory, utilizing the adaptive sampling method for pre-training large language models, which can also be applied to other deep neural networks. Theoretically, we provide a convergence guarantee for these adaptive batch size schedules when using the ADAM optimizer, which is widely recognized for pre-training language models. Previous studies have shown that ADAM generally performs better than SGD for training attention-based language models. Our convergence guarantee adds to the existing knowledge on adaptive batch size schedules for SGD and ADAGRAD. From a practical standpoint, we have developed adaptive batch size schedules using PyTorch FSDP, specifically designed for pre-training large language models with billions of parameters. Regarding related work, large batch training has been effective in various deep learning fields, including computer vision and natural language processing. Many open-source models, like OPT and Llama, have been pre-trained using large numbers of GPUs or TPUs, which naturally leads to large batch training. While large batch sizes are now common, the choice of their size often depends on hardware availability. Recent work on stable LM clarified how to select global batch sizes to balance training time and the number of training tokens needed to achieve the desired loss. Other studies have examined the effects of data parallelism and found that large batch sizes do not harm generalization performance when hyperparameters are carefully tuned. Theoretical models have been developed to understand the critical batch size that balances speed and efficiency in large batch training, particularly for language models. However, most studies have used fixed batch sizes, with one exception exploring dynamic batch sizes in a simple model. The impact of adaptive batch sizes on pre-training language models is still not well understood. We also discuss batch size schedules. Adaptive sampling methods, which modify batch sizes based on gradient noise or approximation quality, have been explored in deep learning but not in the context of data parallelism with distributed samplers. While adaptive batch size schedules are not new, our work is inspired by the heuristic approach of batch size warm-up, commonly used in pre-training large language models and reinforcement learning. This method typically involves starting with smaller batch sizes and gradually increasing them during training. For example, GPT-3 began with a batch size of 32,000 tokens and increased to 3.2 million tokens over the first several billion training tokens. Other models, like Olmo and Llama, have also employed similar warm-up schedules. These batch size strategies have been shown to stabilize training, with few loss spikes and minimal need for intervention. Despite their potential benefits, the effects of batch size warm-up schedules can be challenging to fully understand. Additionally, sequence length warm-up, which gradually increases the sequence length during pre-training, is another related technique. Notably, Llama 3 utilized both batch size and sequence length warm-up in its training process. Section Summary. In this section, we propose adaptive batch size schedules for pre-training large language models, supported by a theoretical convergence guarantee for the Atom optimizer. We also highlight the practical implementation of these schedules using PyTorch FSDP, aiming to enhance training efficiency for models with billions of parameters. Section: Adaptive Batch Size Schedules with 2D Parallelism. In this section, we present adaptive batch size schedules for data and model parallelism, which we refer to as 2D parallelism. This approach helps us scale the pre-training of models that have billions of parameters. We define some notations. We use a specific notation for inner products and norms, and we denote the coordinates of a vector and the partial derivatives of functions accordingly. The ceiling function and the disjoint union of sets are also defined. Next, we consider the empirical risk minimization problem, where our goal is to minimize a loss function expressed as a finite sum. Here, we have individual loss functions and a set of training samples. If the loss function is continuously differentiable, we can express the gradient of the loss and its batch counterpart. The batch gradient is derived from a subset of data points sampled uniformly, and we use this batch gradient to approximate the full gradient when the number of samples is very large. We introduce a norm test, which is part of adaptive sampling methods. This test helps us evaluate how well the batch gradient approximates the full gradient in terms of descent direction. If the loss function is convex, we can determine if the batch gradient is a descent direction based on certain conditions. However, since we cannot directly check these conditions due to the large number of samples, we rely on a batch approximation. We adjust the batch size based on whether the norm test condition is satisfied, increasing the batch size if it is not. This process continues in the training loop, assuming that the next batch will meet the norm test without verification. For data parallelism, we develop a data parallel extension of the norm test, called DDP norm, which can be implemented using PyTorch DDP. Since data samples are distributed across different workers, we need to compute the mean and variance of the gradients from all samples. At each iteration, we split the global batch across workers into equal-sized mini-batches. The mini-batch gradients are computed at each worker, and we use the law of total expectation to find the global batch gradient. When mini-batch sizes exceed the memory limits of the workers, we apply gradient accumulation to simulate larger global batch sizes. Implementing the approximate norm test in deep learning libraries like PyTorch is challenging because we typically only have access to batch gradients. Instead of computing per sample gradients, we propose using the mini-batch gradients to estimate the gradient variance, leading to a more efficient implementation known as DDP norm. This method is computationally efficient since we can easily compute the global batch gradient using all reduce operations, although it does require additional memory and operations for certain calculations. Section Summary. In this section, we present adaptive batch size schedules for 2D parallelism, which enhance the pre-training of large models by efficiently approximating the full gradient using batch gradients. We also introduce a data parallel extension, DDP norm, that allows for effective computation of gradient statistics across multiple workers while managing memory constraints through gradient accumulation. Section: Adaptive batch size schedules with 2D parallelism via PyTorch FSDP. In this section, we discuss how model parallel training allows us to train models with billions of parameters by dividing the model's parameters into smaller parts, or shards, and assigning these to different workers. We utilize PyTorch FSDP, which is similar to DeepSpeed's ZERO3, by replacing the all reduce operation in PyTorch DDP with all gather and reduce scatter operations. We focus on tensor parallelism within model parallelism, combined with data parallelism, ensuring that each worker has its own set of sharded parameters. To compute the microbatch gradient at a worker, we need to reshare the gradients of all parameter shards, which we can efficiently do using the PyTorch FSDP API. We also introduce DDP norm based on PyTorch FSDP, referred to as FSDP norm. In our convergence analysis, we derive guarantees for the Atom optimizer, which is widely used in training deep neural networks. Atom updates parameters using a specific formula that involves a constant learning rate and sequences of moving averages of the gradients. We simplify our analysis by omitting bias corrections but note that they can be included easily. We also consider a more complex scenario where the denominator of the adaptive step sizes is not bounded away from zero. We make several assumptions, including that the loss function is Lipschitz smooth. We establish a coordinate-wise norm test that ensures the expected strong growth condition for the batch gradient. Following a similar analysis as previous work, we present convergence results for Atom under certain conditions. However, our results do not cover the decoupled weight decay in ADAMW, which is often used for language model pre-training, nor do they include aspects like learning rate schedules and gradient clipping. Addressing these factors is complex and will be explored in future work. To demonstrate the capabilities of FSDP norm, we conduct experiments with various decoder-only autoregressive language models of different sizes and pre-training datasets, including Micro Llama 300M, Tiny Llama 1.1b, and Open Llama 3b, all trained on the C4 dataset. We tokenize the C4 dataset using the Llama 2 tokenizer. Our experiments are run on workstations with different GPU configurations, where training the larger models is only possible with PyTorch FSDP. We implement our work using the PyTorch FSDP API and Lightning Fabric for ease of training. We plan to release the open-source implementations of DDP norm and FSDP norm on GitHub once our manuscript is accepted. Section Summary. In this section, we discuss the implementation of model parallel training using PyTorch FSDP, which allows for efficient handling of large models by sharding parameters across workers. We also present convergence guarantees for the Atom optimizer and showcase the scalability of FSDP norm through experiments with various autoregressive language models, highlighting its advantages over traditional PyTorch DDP. Section: Training Specifications. In this section, we outline our training specifications, which follow the pre-training setups of open-source large language models like Tiny Llama and Olmo. We implement a linear warm-up followed by a cosine decay for the learning rate, using the ADAMW optimizer that includes weight decay and gradient clipping. Our adaptive batch size schedule has a maximum global batch size, beyond which we stop norm testing and instead conduct fixed interval testing. We prioritize efficiency by using the original test form rather than its coordinate-wise variant, even though the latter offers convergence guarantees. During the initial training phases, we increase batch sizes to their maximum, but we only pre-train our models with enough samples to demonstrate our method's effectiveness, treating these experiments as proofs of concept. More detailed configurations can be found in the experiment details section. For micro-llama with 300 million parameters, we pre-train it on the C4 dataset using the same hyperparameters to analyze the impact of adaptive batch sizes. We compare it against various constant batch size baselines and a stage-wise batch size schedule. Our results, shown in the corresponding figures and tables, indicate that our proposed DDP norm significantly outperforms constant batch size baselines in terms of validation loss. We find that our method achieves lower validation losses with a similar number of training steps compared to the constant batch sizes. Although our method performs slightly worse than the stage-wise schedule, this is expected due to the latter's smaller average batch size and greater number of training steps. The stage-wise schedule is heuristic and may require extensive tuning. We also notice that our method starts with smaller batches and increases to larger ones later in training, which enhances training efficiency by reducing the total number of steps needed. Importantly, our approach minimizes the negative effects of large batch training, such as higher validation loss at the end, by beginning with small batches and increasing them adaptively. This allows us to benefit from both the good generalization of small batches and the efficiency of large batches. For tiny llama with 1.1 billion parameters, we again pre-train on the C4 dataset, utilizing PyTorch FSDP and FSDP norm. Our findings mirror those from micro-llama, showing that FSDP norm effectively reduces the generalization gap between large and small batches. We can adopt larger batch sizes during later training stages while maintaining competitive validation loss. Finally, for OpenLlama with 3 billion parameters, we pre-train on the C4 dataset using a shorter sequence length due to resource constraints. We observe similar trends as with the smaller models, where our approach requires slightly longer training times and more steps than constant batch sizes, yet achieves lower validation loss. While a constant batch size of 4096 yields an even lower validation loss, it demands significantly more training steps and time. Section Summary. In this section, we outline our training specifications for various models, including micro-llama, tiny llama, and OpenLlama, emphasizing the use of adaptive batch sizes to enhance training efficiency and generalization performance. Our proposed methods consistently outperform constant batch size baselines in terms of validation loss, demonstrating the benefits of starting with smaller batches and increasing them adaptively throughout training. Section: The effect of number 1. In this section, we discuss the impact of the hyperparameter that controls the adaptive batch size schedules. This hyperparameter influences the likelihood of finding a descent direction, which in turn affects how we increase the batch size. Selecting the right value for this hyperparameter is crucial for the success of our method. Through our experiments with different model sizes, we observed that larger values lead to more gradual increases in batch size, while smaller values allow us to fully utilize our computing resources earlier in training, although they may undermine the purpose of adaptive batch sizes. We also note that this hyperparameter is influenced by the base learning rate and the quality of the training datasets. We propose that there are broader scaling laws related to the critical batch size, which affects the quality of gradient approximation and the level of gradient noise. In our experiments, we typically set this hyperparameter low enough to enable rapid increases in global batch sizes, reaching their maximum potential. However, we found that at a specific value, the final batch size was around 3,800, which may represent the critical batch size for that setting. Understanding critical batch sizes in relation to gradient approximation quality is important, and we plan to explore this further in future work. In our concluding remarks, we present an efficient implementation of the norm test in PyTorch for large-scale distributed training, emphasizing hardware efficiency and ease of development. Our implementation demonstrates that adaptive batch size schedules can effectively pre-train Llama 2 language models with up to 3 billion parameters using a limited number of GPS. We also provide convergence guarantees for the norm test with the Atom optimizer, indicating that our adaptive batch size schedules are both practically viable and theoretically sound. Given their generality and scalability, we anticipate widespread adoption of these schedules in pre-training large transformer models, including vision transformers and autoregressive image models. We focus on a PyTorch FSDP approach due to its seamless integration with PyTorch. Additionally, we believe that a more advanced version of these schedules, utilizing the new PyTorch FSDP and tensor parallelism, will greatly improve scalability for training models with over 7 billion parameters. For further details, we encourage exploration of the Torch Titan and Lingua repositories.